Okay, let's close out our discussion by going deeper into the categorization of solids. Remember that we started out by saying that there are two large categories, amorphous and crystalline. Now let's see if we can subdivide the crystalline solids into other categories to account for specific properties, all right? So let's go here to back to our PowerPoint. And we're gonna start by saying that we can classify crystalline solids by A, the kinds of particles that form them, B, by the kinds of attractive forces that hold the particles together. So these are the two major criteria that we're going to use to classify different kinds of crystalline solids. Remember, crystalline solid means that at the atomic or molecular level, they have a well-ordered, you know, arrangement of the particles in repeating patterns. So, of course, we are familiar with ionic compounds. And ever since we were introduced to them, we were told, oh, they arrange the ions in the form of a crystal lattice. And the majority of them can be sub-organized into the types of crystals they form, but in general, we call these ionic crystals. In the ionic crystal, essentially the lattice points, right, the corners of the cube, are occupied by cations and anions, because that's what the ionic crystal is made of, right? We know that the force that holds these things together is electrostatic attraction, so the positive charges attracting the negative charges. These are going to be very hard solids. They're brittle because if you hit them with, like a chisel type of instrument, they will crack along the fractures between the different crystal units. And they have high melting points. They are held together by a very strong attraction, and therefore it takes a lot of energy to melt them. In and of themselves, they're very poor conductors of heat and electricity. Now, of course, if you take an ionic compound and you melt it, when the ions are in that more fluid state of the liquid, they can then conduct electricity a lot more easily. Notice when you look at the three structures here for cesium chloride, zinc sulfide, and calcium fluoride, notice that they're different and they might not always actually fit into the three patterns we discussed earlier, the simple cubic, the body-centered, or the face-centered cubic. So sometimes they don't really fall into it. You can see that cesium chloride would probably qualify as a body-centered cubic cell, but the other ones perhaps follow other kinds of patterns. There are many, many different types of patterns, and actually many crystalline solids are not organized in cubic unit cells. They sometimes have other types of geometric shapes. Another type of crystalline solid, we're going to call them covalent. And this has to do with the fact that in the crystal, the lattice points are occupied by atoms, but they're going to be connected or held together by actual covalent bonds. They have typically high melting points, and they're typically very hard, and they're poor conductors of heat and electricity because there's not a lot of room there for electrons to move or the atoms themselves to move. I'm showing you here the two forms of carbon that are common in nature. On the left, you have diamond. On the right, you have graphite. Notice the difference. If each one of these spheres represents carbon atoms, you can see that in the diamond, the carbons are arranged in a tetrahedral form. In other words, they're sp3 hybridized, and therefore they generate a very compact, very dense structure, which is responsible for how hard diamond is. It is one of the hardest substances known to us. On the right, we see graphite, which is actually the more stable form of carbon. Notice that the carbons in graphite are connected to three other carbons. In other words, they have a trigonal planar arrangement with sp2 hybridization. And you can see that the trigonal planar arrangement generates these layers of carbons that can stack up on each other. Remember that each one of those sp2 hybridized carbons will have some partially occupied p orbitals that are not hybridized. And so it allows room there for some interaction with the layers, above and below, giving you a solid, but a very brittle one. We know that graphite, from your experience with pencils, they break very easily, but they break along very defined fracture lines. The other thing that graphite can do is that although it is not a strong conductor of electricity, because of those electrons being held in those p orbitals, you can get the carbons in graphite to form these molecular orbitals that form like a layer. We call it a band that allows for some conductivity of electricity. And in most batteries, that rod that you see going through the middle of the battery that generates a little stub on one end with a positive end, that actually is typically a rod made of graphite. Okay, the third type of crystal, we're going to call them molecular crystals. As the word suggests, the lattice points here are going to be occupied by molecules. And these molecules are going to be held together by intermolecular forces. We have studied these, at the beginning of this unit. They can be London dispersion forces, they can be dipole-dipole forces, or they can be hydrogen bonding interactions. And depending on the relative strengths, you're going to have a whole different range of how hard these things are. Most of these molecular crystals are soft and they have low melting points. In other words, they melt at relatively low temperatures. And they're also poor conductors of heat and electricity. Beginning, I think, in the pre-lecture that you watch on phase diagrams, we made some comments about the properties of water. This is the structure of ice. Notice that each water molecule, which is bent and a dipole, arranges itself, first of all, to maximize hydrogen bonding interactions with neighboring hydrogens of the hydrogens of neighboring molecules, generating like these hexagonal layers. And then these layers can stack on top of each other via other hydrogen bonding interactions. What is noticeable about ice is that the crystalline structure of ice generates a lot of empty space. That is why liquid water, where the molecules are able to essentially be closer together, liquid water is actually denser than ice, which explains why ice floats on water. Here is another compound that can also form a crystalline solid. This is acetic acid, which is the component of vinegar. And I don't anticipate that you guys can see this very well. I probably should have zoomed in on it. But on the top, you see the kind of the Lewis structure there on the top left in A, and you can see the hydrogen bonding interactions. And you can see in the middle, if you use a ball and stick model, how the hydrogen bonding interaction generates kind of like a zigzag type of structure. And again, in the bottom with the space filling models, you can extend these zigzag structures to generate these stacks that produce the final crystal. Because these molecules are packed in a more compact way, we would anticipate that acetic acid has stronger intermolecular forces and therefore would have a higher melting point, and that is correct. Whereas ice melts at 0 degrees Celsius, acetic acid typically dissolves around, 14, 15 degrees. All right. The fourth type of crystal we're going to discuss is the metallic crystal. And again, these come in different ways, but we discussed earlier how the lattice points in these crystals will be occupied by metal atoms, correct? They would be held together by something that we called a metallic bond. Of course, metals are typically hard. There are some softer ones. For example, in general, tin is considered a soft metal, Mercury is actually a liquid. They have low to high melting points, mostly high, and they are good conductors of heat and electricity. The explanation of that requires a little further research, and I want to leave that up to you guys. I'll show you at the end what I'm talking about. So remember that our model for a metallic crystal is that what you have is you have a nucleus with a core of the inner shell electrons essentially spread out, and these would form the lattice points of the crystal structure. And then the valence electrons are pooled amongst all the atoms in the sample, generating what we've called a sea of electrons. That is what allows the metals to be such good conductors of electricity, since those electrons in the valence shells are not held tightly to each individual atom, but they are pooled across the structure of the metal. If I apply a voltage across here, it'll be easy to move those electrons from the negative towards the positive pole of that voltage field. The last large category of solids is the so-called amorphous solids. These are the ones that do not possess a well-defined arrangement or any long-range molecular order. One interesting observation here is glass. Because the word crystal is sometimes associated with glass, we might think that glasses are crystalline solids, but they actually are not. The majority of glasses are just fusions of different materials. You cool them after you melt, you melt them, you mix them, you cool them to some kind of a rigid state. They do not form a crystalline structure. You can see on the right side picture here, quartz glass, and you can see how the particles here, which are pretty much mostly silicates, oxides of silicon, they are not arranged in a well-defined order. The positions are not predictable. That is the majority of glasses. That's what they are. Now, they are transparent, but that's an optical property. That is not essentially a property of them having to be crystals in order to be transparent. Now, you can actually produce crystalline quartz. In other words, you can produce glasses that are crystalline. So, crystalline glasses are, some glasses are crystalline, but not all glasses are crystalline. And you see one here on the left side, a crystalline quartz glass, again, made of oxides of silicon, something like silicates. And you can see how they're arranged in a very regular, well-ordered pattern. When you get the study guide for our final exam, you'll be able to see what are the things that you need to know and which ones are, extra knowledge, extra material that you are not responsible for. We have covered a lot of material here, but we will close it out here. This will be a shorter session. So there's one more topic that I need you to study on your own. I just don't have a good way of explaining it here via this remote instruction. Hopefully at some point I'll have a good set of animations and simulations to display this. So on your own, please go to your Tro book. And if you're in the 5th edition, this would be section 13.8. There's something called band theory that is used to explain electrical conductivity. So I'll have you study that on your own. Please do that. If you have questions, you can ask me. Again, when the study guide comes up on Canvas, you'll be able to see exactly what topics or what aspects of this theory and process of conductivity you are supposed to know. All right.